Well, hello again everybody. Well, today in the workshop we're going to be taking another look at our master radio, which is the D110W. Well, in last week's video we did actually talk a little bit about the resistive mains cord, and I actually went ahead and cut that off, and we've got to come up with something to deal with that. So these types of radios, as I said last time, they're actually known by a few names. I think the Americans used to call them midget sets because they're quite small. Some people call them, I think they call them bedside radio set. I think the idea was that, you would have a main radio in your lounge, but if you were quite well-to-do, you'd probably also have another radio in the bedroom on the bedside cabinet or something like that. And of course that would have to be a lot smaller. I mean, the whole idea of, for example, a bedside radio, well, it's not something that would occur to a young man, is it? When you first 5 years of marriage, there's quite a lot of bed bumping and rocking going on, and then by 10 years in, most of the bed rocking is finished. But by 15 years in, the conversation's gone as well. So really you need something to fill its place, and I guess that is really the reason for these bedside radios. But the other thing about them is, because they were quite compact in space, one of the things they did to reduce the size and space was they removed the mains transformer and put the resistive line cord on them. Now, I did actually talk about those resistive line cords. They certainly did have a reputation for setting on fire, especially on older sets that had maybe been slightly abused. But the other problem with the AC/DC sets like this is potentially the chassis can be live, so that somebody who doesn't know what they're doing, they could go in to do a repair, touch something and end up with a really nasty electric shock. Now, the chassis wouldn't necessarily always be live. What they tried to do is they would try to connect the chassis to the neutral line, but the problem would be especially in the early days in the UK in the 1930s and 40s, a lot of the main sockets were unpolarised. You could actually put the plug in either way, so about 50% of the time the chassis would be at neutral, so effectively at earth, and the other 50% of the time it would be live. Now, it wouldn't be so bad for you and me. You know what you're doing with radios. You know about the dangers of an AC/DC set, but the average housewife, or perhaps the average Joe Bloggs now, who buys one of these radios, getting on for 60 years later, he hasn't got the experience to know that the dangers that these can present you with. So if you're going to work on an AC/DC set, it's quite important to look after your own safety. So one thing that I will be doing when I power this radio up, will be working from an isolation transformer, which makes it less likely to get an electric shock. You can still get a really nasty electric shock even using an isolation transformer, but certainly to use one does make it safer. But for the average Joe Bloggs at home, they wouldn't know about the dangers, and even something like a knob falling off the radio, we've all occasionally pulled a radio knob and it's come off in our hands. So if a knob was to fall off this radio, you would have sticking out the front this brass shaft, and again, depending on which way the radio was plugged in, this could be live. And this is normally held on by a little grub screw. Yeah, that's still in there, I can just about see it. So this would be fitted on the radio like this. Now, one of the things that the manufacturers used to do, once it actually fitted the radio knob and tightened this grub screw up properly, they would actually fill the hole at the one side of the knob. They'd fill that with some hard wax, and what that would do is it would just stop the average Joe Bloggs from getting a screwdriver and taking the knob out and exposing this potentially live shaft. So that's one of the little things that they did. Now, some of the other precautions that were made were to actually put the radio chassis into a really tight fitting box, so there wasn't room to get little pokey fingers in. And in fact, this radio itself does have it has a back on it, and it's got relatively small ventilation holes in it. So again, that's just to stop you being exposed to these potentially live metal parts, because again, I will say that if somebody managed to put the plug in the wrong way around into the socket, which was quite possible, this whole chassis could be live. Now, you may think that you've got modern 3-pin plugs in the UK. Of course, they're polarised, So in theory the live and the neutral should be correct, but it certainly isn't unknown to find in houses that the sockets are wired up incorrectly. You know, you can have the live and the neutral swapped over, all your appliances will work perfectly well and you would never know. Well, you wouldn't actually know until you got a reminder from touching the live chassis on one of these radios. So I don't think I'm going to bang on much more about the safety aspects of these radios. What I would just say is, because it doesn't have a transformer, if you find a radio that doesn't have a transformer in it, just think about that. Think about, you know, you need to take some special precautions to look after not just your safety. You know, you've also got a duty that when you're pushing up the daisies in a field somewhere, this radio is going to get passed on for somebody else, and that somebody else is probably going to have much less experience than you have. So you've kind of got a duty of care for people in the future to try to keep them safe. So whenever you're working on a radio, you've got to think about that as well. So as well as some of the very obvious dangers associated with a potentially live chassis, there's also some less obvious dangers which really just come as a result of having a direct connection to the mains. Whenever you've got a transformer in a radio set, that does actually give you a little bit of protection from the mains voltage side of things, because you can only pull so much current from a transformer winding, whereas you've got a direct connection to the mains here potentially. You've got less protection. So here's an example of that, in that this is the antenna wire that comes with a radio, and it is just a piece of wire that's probably, I don't know, 6 feet long or something like that, and it's just soldered on. Well, again, it wouldn't be unusual for, if you get a mains fault, for you to get potentially quite high voltages. Now, the end of this aerial wire, when I got it, it had actually got the ends of the wires stripped on it, so somebody had bared the wires and stripped them, because I suspect what they were trying to do is they were trying to get better reception. So everybody, you know, you want better reception, you want a longer antenna wire. So somebody had stripped the end of the wire and just twisted them together. But the only thing that's really protecting this end of the aerial from mains high voltages is this capacitor here. Now, it looks like this is a mica capacitor, and they are very, very reliable by general mica capacitors, but I would probably be looking at replacing this with a safety rated capacitor. I use the dual rated XY type capacitors now, so if you've ever got a terminal which takes, you know, whether it feeds a signal in or out of the radio, you know, you sometimes have plugs and sockets on the back of a radio. You don't just want to connect those plugs and sockets with any old capacitor. You want to connect them with a capacitor that's going to be very, very reliable in operation, because what you don't want the capacitor to fail and potentially put live voltages on any output connectors or any wire antenna like this. So yeah, we're going to replace this this mica capacitor. I think it is a mica one. We're going to replace that with an appropriate rated, safety rated capacitor. Also on here somewhere we're going to have an across the mains capacitor, I think. So again, we're going to dig that out and replace that one. Of course, we're definitely going to replace, I think I mentioned it last time, C16, which will be any grid coupling capacitor really. And then on the top of the radio we've got the output transformer, and this has got a little waxy capacitor on it. These generally should be replaced as a matter of course as well, because if they fail, they will probably again damage your output valve, which, you know, an output valve is expensive and a capacitor is very cheap. Now, the reason you should replace it is because it is a capacitor which is quite highly stressed in its operation. I'm guessing that you get a little bit of a flyback effect from having this big wound inductor here. So the rating for this capacitor should be at least twice the supply voltage of the radio and higher if you've got it. So the purpose of this capacitor, it's just to roll off any high frequencies, make the radio sound a little bit less shrill, and I suspect it might also maybe help prevent the radio from going into some kind of oscillation mode. So that's what it is. It's a capacitor to roll off the high frequency response. So what I've decided to do is, rather than just go ahead and replace all the capacitors on site with something, potentially some of these capacitors are getting quite expensive now. What I've done is I've rummaged through my capacitor drawer, and I had a lot of miscellaneous capacitors for one reason or another. They had short legs on them and stuff like that, because you know it's not unknown to start a radio restoration. You get halfway through it and then you find some broken component which can't be replaced, or you find some damage, and unfortunately that just brings the restoration to a halt. So I had quite a few capacitors which I'd salvaged out of my failures, and I've got them here. So what I've decided to do was I've taken a few old capacitors and I've soldered some lengths of wire on them like this, and I'm going to use them just to temporarily. I'm going to cut out some of the old components and I'm just going to tack these into place. So we've got some of the typical type, what's that, 0.01 microfarad, so that's kind of a typical side for a grid coupling capacitor. And I've also got some electrolytics. I've got a 33 microfarad there and a 22 microfarad. I've even gone ahead and I've taken some capacitors and I've just wired them onto some flexible leads like this, and again we can just, so these in here are electrolytic capacitors. That's an electrolytic, that's another electrolytic, and again these are just typical grid coupling caps. So what I could do potentially is I can cut a dubious bad looking capacitor out of the way, and just for testing purposes I can just clip these in like so. So the other thing that I did with these electrolytics before I actually sealed them up in this this heat shrink material, I took some 300 kilo ohm resistors, I think they might have been 300 or 400 kilo ohms, and I wired them in parallel across the capacitors. My thoughts were being that if I actually unclip this from a radio, potentially this capacitor could still be charged up, and it would be lying around on my bench with these exposed terminals, these crocodile clips, and of course it wouldn't be long before my fingers just naturally found their way across them, and it would probably make me squeal somewhat. So I went ahead and I've just put some resistors across here to just to discharge, some discharge resistors, just to take the high voltage off these in a relatively short amount of time. So we're going to go ahead and I'm going to play with these today. It's kind of a new idea for me, so I want to see how it works out. Oh dear, I seem to have a dial cord explosion. Oh dear, that's definitely going to stop the restoration because I'm rubbish at dial cords. Well, I think to start with today I'm going to go ahead and I'm just going to disconnect this main electrolytic because it's very bulgy and it's clearly been leaking electrolyte at some point. So let's get that out of here. So of course we can see, looking at the ends of this capacitor, it has been leaking electrolyte from both ends and it's definitely looking very, very bulgy. So I'm going to replace this regardless of what the reading says. But I think we will go ahead and we'll just check it on our ESR meter. Looking at the age on this, it's actually younger than I thought it was. This says January 1949. Well, I actually thought this radio was a 1946 radio, so I'm not exactly sure about that. I'll leave it up to you to decide if it is it original or a replacement part. Certainly the soldering on one end of it did look a little bit dubious. Let's try it on the SR meter. Let's try the yellow sections first, which should be 16 microfarad. Okay, so it should be 16. It's coming up as 31 microfarad with an ESR of 0.54. The ESR probably isn't totally terrible, but the fact it's double its capacitance, that means it's on the way out, because that's one of the failure modes of electrolytics. They go high in capacitance as the electrolyte dries out. Let's try the other section, which should be 24 microfarad. And it's actually 34 microfarad. That's gone up quite a bit. That might still be in tolerance, but what's the ESR? The ESR isn't totally awful, 0.4. But yeah, we're going to replace this. So that's the first job. Okay, just taking a quick look at my circuit diagram, I can see that this radio employs what they call LC smoothing. So it's got two capacitors that are in the same can, and they're in series with an inductor, our L1 here. So we need to put C21, that is the 16 microfarad segment, and C20 is the 24 microfarad. So here's a 15, and we should have a 22. Have we got a 22? I thought I had a 22. Oh yeah, 22 microfarads. So these two are just going to be tacked on here, and these are going to be the temporary replacements for the capacitor that we've just taken out. So I've got to admit, I'm not sure if this idea that I've got for just tacking on components in this way, I don't actually know if it's a good idea or not. It's it's just one of them little experiments that sometimes you try. Ooh, he said dropping the nut. Yeah, it's just one of them experiments that you try. This could turn out to be you know, a stupid idea. I have a lot of stupid ideas, but I just thought it was worth giving it a try, seeing what we think. This is going to drive me nuts. Nuts. Okay, so just looking at this capacitor that appears to be a bit burnt. This one is a C4. I'm just looking at this. This is this is connected to the mixer valve V1, and it's a cathode bypass capacitor. So generally these are pretty lightly loaded, and I'm trying to see, well, there's no reason why this should have been damaged, because they don't see a great deal of voltage across them. Just trying to think, is that burn or is it? I think that is burnt. So yeah, I'm afraid I think we have got to just take this out as well. So yeah, I am going to cut it out. I was going to say it might just be dirt on the wax, but I do think it's burnt, so that is going to come out. So I'm just taking a look at our 0.1 microfarad capacitor that I removed, and I'm just trying to see if it is burnt or if it's just like dirt in the wax. Yeah, I think it actually is burnt. Yeah, whatever the dark spot is, I suppose it might not be burnt, it could maybe be something leaking out of the capacitor. Don't know. Shall we try it on a capacitance meter, see what that says? Okay, so it's coming up as 150 nanofarads rather than 100, but I suspect the issue would probably be leakage. Let's try it at 250 volts first. Okay, so 0.3 of a megohm, so that is you know, that is leaking, that's low. It should reach infinity for that. Let's try it at 500 volts. 0.3 again, let's really fry it, let's try it at 1000 volts. 0.1. So okay, so that is not good. And let's just do a comparison with a new capacitor, because I'm sure you want to make sure I'm not fibbing to you. So here's just a random capacitor out of my drawer. And that reads infinity, so there's absolutely no leakage across that. Okay, so I'm just taking a look at what other capacitors we should change out, and just notice we've got C23, that's got the full rectified HT across it. Just struggling to find it. Can anybody see C23? Oh, there it is, right, hiding in plain sight. So C23, this is C23, and it does look again very black and dodgy looking. It doesn't look very good. Okay, and so it's 180 nanofarad, so it's about twice its value. Okay, so 0.1 of a meg, so 100k, so again, that is bad, it's leaking. So as you can see, I've gone ahead and I've replaced some of these waxy capacitors. I haven't replaced them all by any means, but the ones which are kind of most likely to give us grief and explode in my face, we've changed them out, including this these two electrolytic capacitors. They're kind of blowing around in the breeze a bit how are you doing, but I think they'll be fine. We replaced the one across the output transformer, and while I was playing with it, I had to solder a wire back on, and I also just injected some audio into one side of the output transformer, and I could hear it at low level in the speaker, so it looks like we've got a good audio output transformer and we've got a good speaker, because if either of them two things are bad, again, it can really spoil your day. So I think we're about now at the point where we actually want to put some power onto this radio. So originally it had that horrible evil resistive line cord, which basically just consists of a 600 ohm resistor which was centre tapped in the middle. So as you can see here, I've bought some a couple of wire wound resistors, and I have just mounted them to a piece of metal, because I'm not exactly sure how hot these will get yet. I did do a rough estimation of the wattage, and I don't think they are going to get much above being warm, but yeah, you've got to try these things out, haven't you? So let's go ahead and connect our neutral wire, and interestingly enough, this radio does actually employ neutral switching, which is another potential danger with these sets, because what can happen is when you do actually disconnect the neutral, of course the chassis does get pulled up to the live mains potential by this bank of resistors here. It actually goes through the valve filaments and it will actually pull the chassis up to your full 240. So another dodge, you actually, when you switch it off, the radio actually becomes more unsafe, which is another trap for young players. Okay, so the next connection we've got to do is actually the centre tap point from our resistive divider, and that goes to the anode connection on our rectifier. So let me just, there's just a huge gob of solder on here. In fact, this gob of solder is unfeasibly massive and large. Let's see if we can just do something about this. And I think while I'm in here I need to sort out this capacitor C18. For some reason I thought I'd already done this one. I must have managed to confuse myself. I was sure I'd changed that out. This one comes across the main incoming supply between live and neutral. So again, this one wants to be changed out, and ideally it would be changed out with a capacitor with a safety rated capacitor, another X-rated capacitor, because it goes across the mains. Remember, that's what X stands for across. So we need to put some valves in now. So we've got a rectifier valve here. Now I did actually get this rectifier valve out earlier, and amazingly enough, well, not surprisingly I guess, the filament would actually burnt out on it. So I'm guessing that that's probably what shut this radio down. Somebody had attempted to replace that resistive line cord, and they put this bodgy resistor inside, and obviously they hadn't done a very good job, and I think they did manage to burn out the filament of the rectifier. But as it happened, and very luckily, I went through the hoard and I managed to find another rectifier, which I think should be in here somewhere. Is that it? Yep, here it is. 35 Z4 GT and 35 Z4 GT. So we will replace that. So the next valve is V4, which is 35 L6 GT, which is our output valve. Now interestingly enough, what the 35 denotes on here is the first letters, first couple of numbers. That's the voltage. So both the rectifier valve and the output valve actually have 35 volts across them. Now they actually have, of course, the current runs in series with all the filaments, so they have the same current. But what it actually means is the heater supply is going to have more wattage. So I'm wondering if the reason that the rectifier and the output valve, if they have a higher wattage filament, is because they need greater amounts of emission. I'm thinking that could be the case, but I'm not certain. So V3 is our detector, and that's a 12Q7 GT. 12Q, where has it gone? Oh, don't appear to have one. 12K7, 12Q7, here it is. 12Q7 GT. So the next valve is V2, which is a 12K7 GT. 12K7 GT, which I'm guessing is our intermediate frequency amplifier. So let's put that in. And finally, I'm guessing this is our mixer valve, 12K8. All this top cap wiring is really crumbly, it's in a bit of a mess. Hopefully it will stay working long enough just to give this thing a test. I'm actually going to run it up on the variac, which we've got here, but the variac is actually plugged in on my isolation transformer, so it may look like I've just got an ordinary plug socket at the back of my bench, but that's actually an isolation transformer. So what we're going to do is we're going to run it up gradually. So we've got a meter here, that's measuring the total AC voltage across the valve filaments. So I'm expecting about 112 volts. That's what we should get when this thing's at its full 240 volts, somewhere around there. And then this other meter that we've got here is measuring the B plus, the rectified output voltage. So I guess all we need to do is start to turn this up. Now, is the radio turned on or off? Let's turn the volume fully up. Okay, something's not quite right there. Going to turn off. And actually it seemed to be a dial lamp that was flickering on and off very brightly. So I'm just going to make sure we're unplugged and have another go. Well, these resistors are actually getting quite warm now, so something was happening there. Okay, when I powered it up last time I could see that the rectifier valve was kind of flashing, it was kind of flashing a blue colour, and when you actually see a rectifier flashing like a purpley blue, it means it's supplying excessive current. And I should have known really, because for whatever reason we could also see that our B plus voltage really wasn't coming up. It was around 12 volts or something. So what I've done is I've just gone ahead and we've got the DC voltmeter, which is this one here. We've got the DC voltmeter connected to the anode of our rectifier valve, so we can see the smooth DC coming out of it, but we've actually got the anode disconnected from the rest of the circuit. So there's something in this circuit which has got a short, there's something in this radio set which is pulling our B plus to, I'm not going to say to ground because it's not a short circuit, but it is pulling it down. So I'm afraid all we can do is plug in and tentatively try again. I mean, basically I'm just, at this stage we've got everything disconnected out of circuit, so hopefully we should just see our anode voltage come straight up. Well, I've just spent the last hour trying to chase down some shenanigans, and I think what the problem was with this radio, I actually thought that we had a short on the HT, but I'm not so sure. I think it's actually just a bad valve, because what I've actually done is I've actually replaced the valve rectifier with just a diode and a resistor, and I've put that in, and the radio seems to be working perfectly well. So I've got here a brand new old stock valve, and that really is a thing of beauty. I think it might be the first time I've ever had a brand new valve, so I've just destroyed that, haven't I? So in theory the DC output from these particular valves is around 100 milliamps. So what I think we'll do is we'll disconnect the solid state rectifier. I'm going to swap out the valve and we'll switch it on again, and when we switch it on again we'll monitor the current and we'll see what it's like, because it will be interesting if all this messing about has just been down to a bad valve. It's funny, it doesn't seem to have a valve number on it. Oh, it is written on the top, 35Z4GT. So let's take the old valve out and put the new one in. So that's our DC volts, and now I'm going to take the output, the DC output from our valve, I'm going to take that, that's going to go through this meter here, this Ryobi meter, which is set to measure current in milliamps. So we need to see if I can get the wire to stay on there. Will it stay on there? Please stay. And then into our reservoir capacitor. And in theory we can plug in and switch on. Shall we run it up slowly? No, let's throw caution to the wind and switch on. So we've got no volts at the moment. Nothing seems to be lighting up. Okay, so we've just gone ahead and installed our absolutely brand new valve, and it doesn't work. So our brand new valve that's just come new out of the box has an open circuit heater chain. So some days you really just can't catch a break, can you? Let's go back to the original one. That's fine. You know what, I'm absolutely furious about that. Furious. So it looks like, unfortunately, our brand new lovely RCA valve, lovely looking valve in a brand new box, it's got an open circuit heater chain, so that is absolutely no use. So what we're going to have to do is we're going to have to put our other faulty valve in, which is obviously very low emission. It's got no current output, so we need it in circuit just to complete the heater chain to power up the rest of the valves. So we're going to put this back in, and I'm just going to temporarily reinstate our solid state rectifier, and I'm afraid that's going to have to work like that until we can order yet another valve. So there was 15 quid plus postage down the drain. Just to keep going on this, we're going to have to solder in our diode again, which is it's a 1N4007, which is a 1000 volt rated diode. It's also got about, I don't know, I think there's about 150 ohms of resistance in here, because valves are a little bit soft compared with modern solid state rectifiers, so you need a little bit of resistance in there to drop a little bit of voltage. So we'll stick this diode back into circuit. We've got the old output from our normal rectifier valve. I've just got a piece of tape around that at the moment, so that's going to have to stay taped off and just pushed out of the way until we can get another valve. I really thought I could make some progress with that today, but it looks like not. That's really annoying, really is annoying. Okay, let's turn the power on and see if we've got some HT this time.
I mean, that is particularly interesting, isn't it? Because the government were unequivocal then that that's what was going to happen. And it didn't happen, and there are many schools that still have.
Okay, so we got some audio out of our radio there. Now, one problem I also found is, unfortunately, the frequency changer valve is also bad on this. Or rather, it's not the valve, it's this socket here. This socket is absolutely awful. The slightest touch, it comes out of circuit. And what I'm going to have to do at some point in the future, I'm going to have to take this valve socket off. And sod's law, it's the most complicated valve socket in there, which is, you know, it's a frequency changer stroke mixer valve. So we've got to change the socket because they really are quite cheap and nasty kind of. Is it Poxolin? I don't know. They look like Bakelite, like sheets of Bakelite, very cheaply made sockets, and they're not bolted in, they're riveted in. So we're going to have to grind the rivets out. Disconnect all the wiring and change that because it's just making an intermittent connection, and I think that's part of the reason the audio isn't particularly good. Let's turn it on and have another go.
You wonder how much longer this will continue in its current form, whether things need to evolve.
Yeah, I mean, they already dropped weekend press conferences because some scientific experts front up some of the time. You know, sometimes it's just the minister on their own, sometimes there are other people there. But I think there will be questions if it turns increasingly into just a ministerial broadcast. Some people will perhaps suggest that it's a bit of a political broadcast, not so much that scientific public information campaign where people need to hear the latest.
In skills and lifetime wages, so that, for example, on average these
that many fans just aren't aware of the song's links to slavery. It says it needs to do more to improve diversity after the Black Lives Matter protest, and it suggested that the song was first sung at Twickenham when Martin Chariots of Fire was playing at the Middlesex 7.
Well, so far this little master radio really has led me a merry dance. I spent ages trying to track down the HT problem. It does turn out to just be a bad valve that's low emission. So I order a brand new valve, that arrives, we plug it in, and the filament, the heater, is open circuit. So we've gone ahead and we've put our solid state rectifier valve in. We found that the radio does work, although we've got a really dodgy valve socket that we now need to replace. So I've got to admit, some days you have a good day in the workshop, some days you have a bad day and just want to throw the radio against the wall. Well, today's not been such a good day, let's put it that way. Well, at the end of the day, it's only radio repair, it's not life and death, and I'm sure my old gran would have said worse things happen at sea. Well, the other thing that's actually quite surprised me about the radio is how much power is being dissipated in these two power resistors that we've got to replace our resistance line card. Now, I think I estimated that it was going to be around 18 watts, and I've carried out some measurements, and it's actually closer to 21 watts. Now, that could be that my mains voltage here is particularly high at the moment, because I do kind of usually set the variac here to represent what my mains voltage is. So it was nearer to 21 watts because my main voltage is, for whatever reason, it's nearly 250 volts today. It does go up and down a bit, but of course the higher the mains voltage, the more dissipation in these resistors. And again, it just made me think at how much power is actually being dissipated in our old resistance line card. Now, I suppose that the old resistance line card was about 6 feet long, so that is quite a long length of wire to dissipate those that heat in. But these two 50 watt resistors here, they get toasty hot, they really do. You can't keep your hand on them. So as it turns out, because there is so much heat given off by these resistors, I think I will go ahead and I'm going to have a go at designing a capacitive dropper. They also call them wattless droppers because they don't actually get hot in operation. I've never actually had a go at designing one of them before, so it will be quite interesting. And at the end of the day, this is just a crappy old radio. If something goes wrong, something goes wrong, doesn't it? It's all part of learning and the radio journey. So I think that's what I will do when we come back next week. So for me, I've got to go away and buy yet another valve, do some calculations to do this wattless dropper, and I think for now I will see you all next week. So that'll do. Stay well, hope to see you again very soon, but until then, bye bye for now.